G-Unk.
I go.
Are we going?
Yep.
Okay. Well, I'm Matthew Stab now. Today we'll be going over terminal velocity and falling squirrels. So we're going over this concept, doing a fun little application with our humble little flying squirrel of artistic depiction. So going over what terminal velocity is. So terminal velocity is the velocity at which during free fall you stop accelerating because your drag force has equaled the force of gravity pulling you down. So that means net force is 0 because Fg is counteracted by Fd. So, I don't know, I didn't draw that perfectly to scale, but these are supposed to be perfectly equal but in opposite directions. So, net force equals 0 because Fg and Fd, drag force, are equal. So, when you're falling, say you're skydiving, at a certain point you're going so fast that the drag force pushing up on you, resisting your motion, is enough to counteract gravity and you will stop accelerating downwards. So your velocity will be constant. So we're going to go over the drag force equation, which equals our force of gravity, which is just simply mg, mass times your acceleration due to Earth's gravity. But that's the easy one, there's a harder one. So we begin with 1/2 times your other variables, and we have Greek letter rho. It's not a P, it's a stand-in for density. Of course, Earth's air density is not really constant, so as you go closer to the ground, it's more dense. So for this, I took more of an estimate. If we were to take like averages over a certain distance, then that's kind of what we did. We took the average, but there's more complex ways to find a more accurate answer, but we're keeping it simple. And then next is our velocity squared. So an example I'm going to use to bring up drag force is when you're in a car and you stick your hand out a window, that force you feel as you're moving, the force of the air pushing against you, that is the drag force. So if you're going in a fast car, it's going to push more than if you're in a slow car. Next is our drag coefficient. This is a value that is pretty hard to find. For our squirrel example, we're estimating it to be the same, the value for like a sheet, like just a plain rectangular face. So it kind of like correlates to the profile, the shape of your object. So like, I don't know, like a ball versus like a block. If a ball is going to move through the air easier than like just a block with its square face. So that value just correlates to that. And for example, we're taking the drag coefficient of like a sheet of paper. You can look those up and look at those. It's pretty cool for the different objects. Lower means more aerodynamic. Then our last value is the area. It's kind of straightforward. Like if you have like a bigger area sticking out the window of your car, it's going to push harder than if like you just stick your hand out. Or if you stick out like your hand like this, it's going to have less area. And then also your hand from this profile is like rounded. It's more presentable than just a flat surface. So this also would affect your drag coefficient. So we set these equal to each other and we're trying to find the velocity. So we're going to manipulate our equation. So I did this already, I'm kind of cheating. But if we manipulate our equation, we get this, a value for V equals. I already have these values, I gathered these, their mass. These are all just off the internet, values for properties of the atmosphere and Earth and our flying squirrel. So yeah, I'll plug these in a calculator. May I have my calculator, please? My trusty assistants are working. So plug in this expression and find take this one, thank you. I'm going to take real quick, square root fraction 2. Let's see how fast I can put this in calc. Short for calculator.
What?
Alright, so this gives us a value of 4.41 meters per second. Oh, got it right. Meters per second squared. Unit for acceleration, we're finding velocity, so it's meters per second. So, using this, we found that the terminal velocity of a flying squirrel is 4.41 meters per second. If you Google it, our value is not the same as what pops up on Google. These values might be screwed up. Yeah, I don't know. Not really a reliable way to find the area for squirrels like the stomach. But this is the velocity at which a squirrel flying down from his tree, gliding down. He'll be going that fast and he'll stop accelerating and he'll just cruise at that speed. A flying squirrel. So that's the end of the video right there. Hope you enjoyed it.